Good, we're ready to restart. Is the audio correct? Does anyone from group A or B hear me? Yes, yes, yes. Okay, that was a broadcast question or multicast question to group A and B. So we were discussing the types of IP addresses. So those are addresses allocated. So how does address allocation work? Well, there are regional entities, regional means one for Europe, one for Asia, etc., who receive blocks of addresses from this block and allocate it to internet service providers. So if you and me want to receive a block of address, we will need to go through an internet service provider like Swisscom, AT&T, Switch, etc. And then this service provider will allocate a block to the different customers. There are other mechanisms. For example, there is a block of addresses that is reserved for provider-independent addresses. This would be typically for large organizations that want to, like CERN or perhaps EPFL or other entities who would like to have an address and don't want to be bound to a specific provider. We will see, probably you have used already those addresses. So the 2001/32 is reserved for Teredo, which is a way of transporting IPv6 packets in IPv4 packets, which is what we do if, for example, we're at EPFL on the Wi-Fi network that has only IPv4 and we still want to test IPv6, then we can access the IPv6 internet because there are routers in the IPv6 internet that provide a tunneling mechanism, which a tunnel means a way of putting IPv6 packets in IPv4 packets. This block here, /32, means what? 2001, that is how many bits? Well, this is 4 hex, so it's 16 bits. So one piece is 16 bits. So this is 2 pieces. So that means 2001 followed by 4 zeros. If you see an address like this, it's a Teredo address. In the lab, we call it Miredo. That's the name of Teredo in Linux. And this is an example where the address is very specific. It carries a semantic. It means if you see such an address, it's a tunnel. You know it's a tunnel just by analyzing the first 32 bits. And that is used, for example, if a Teredo host speaks to another Teredo host using IPv6, they know, oh, I am Teredo, because my address, I know from my configuration, I'm Teredo. I'm sending to another host that's also Teredo. So we are both, in fact, on IPv4. So I should take a shortcut and create an automatic tunnel via IPv4 directly to this without going to the IPv6. So that's one of the reasons to allocate a specific prefix to tunnel. There are other forms of tunnels, for example, 624, 6RD, etc. 624 is a universal tunneling mechanism that has this prefix, so 2002. As you can guess, this was standardized in 2002 and Teredo in 2001. There are other tunnels, probably if you have IPv6 at home on the wired service from Swisscom, Sunrise, you probably have a tunnel, which is a managed tunnel, but this one doesn't have a well-known prefix. Then IPv6 makes abundant use of special addresses. Special addresses are the loopback address. There were many questions on the chat about why in IPv4 we have 24 bits of prefix for loopback when in reality we use only 1. Well, this is how things are. When people designed this, they thought it's a good idea to have multiple loopback addresses. In practice, people used only 1. So for IPv6, where there is only 1, the loopback address is 1. So this double column 1 means 127 zeros followed by 1. That means this host, right? And this, the empty string, means 0. It means no address. Same convention as with IPv4. Then there are what is called unique local address. The Previous addresses were called unique global. The unique local are private addresses. In IPv4, we call them private. For example, that replaces the 10 dot something. The difference here is that we give a prefix of 7 bits, which means that we have a huge space for unique local addresses. And one use case of this is companies like to have private addresses and private networks. Can you guess why? For IPv4, because there's not enough addresses. I mean, IPv4 addresses are rare, they are expensive. If you have a company with 3,000 computers or 10,000, I mean, a campus like EPFL has probably several tens of thousands of computers. You may not want to have 10 or 20,000 public addresses. EPFL has, because EPFL was very early, got its address, in fact, before switch existed. So it has a block of IPv4 address that it requested very, very long ago, at a time when the internet was not very much known by the public. But if you came later, you didn't have that many addresses. So one reason is you don't want to give a public address to every machine you have because it costs money. But there's another, even more fundamental reason, is you don't want all of your internal network to be visible to the outside. So you want it to be truly private in the sense it's hidden. So those are hidden addresses, and the space can be quasi as large as the public address, which means that you can create a private network that has exactly the same addresses except the first 7 bits as for the public or for the private addresses here. Why do we want that? Well, one thing that happens in the real world outside academia is that networks tend to merge and split. Companies are unstable entities that tend to merge, buy, sell, disappear. So when company A buys company B, typically they merge their networks. Both were using private addresses internally with probably the same prefixes. So you need to renumber everything when you merge to private networks. With this huge space that we have, you can avoid that. So if EPFL would merge with ETH, we have a different prefix for private EPFL addresses, so we could keep these addresses unchanged. In fact, we have several EPFL private networks. We have one for the Smart Grid project, one for other projects, so you can have as many as you want, and they would have different prefixes, so they can be merged eventually in a larger network. So that's the very first difference. Like with IPv4, there are also linked local addresses. I said like IPv4, in fact it's not like, it's very different. IPv6 linked local address are always used. So the first thing that an IPv6 machine does when it boots and activates an IPv6 interface is to check that and create an IPv6 linked local address. So it will always have a linked local address, and there are mechanisms to make sure that those are valid addresses. Being linked local means that collisions are possible. It's possible that 2 IPv6 machines in the world have the same linked local address as long as they are not in the same LAN. Because linked local addresses can be used as destination addresses only for destinations that are in the same LAN. This is key to plug and play. This is key to making networks be plug and play. I mean, historically, the first plug and play networks were AppleTalk networks from Apple. If you would buy a Macintosh in the 90s, you would connect 3 Macintoshes, a printer, a file server. You would connect all of them together without configuring anything. You would not configure an IP. If you do that with IP today, you need to think and know what numbering plan you have. You need to decide on the length of the prefix. And as we will discuss, have a DHCP server that will decide on an allocation for every subnet. You will need to say which subnet receives which prefix. With AppleTalk, you didn't have that. It was done all automatically. And here we have some of this inside the local area network, at least inside the same LAN. You can have your linked local address automatically allocated. So your printer will be able to talk to your computer without anybody configuring anything. Then we have the multicast addresses. Multicast are the addresses that are in this block. /8 means 2 hex digits. So any address that starts with FF. You recognize the all ones, that is invariably used with the meaning of multicast, broadcast originally. Multicast addresses are also used heavily in IPv6, much, much more than in IPv4. In IPv4, they are more or less peripheral. In IPv6, they're used all the time. For example, there is the all link local routers. So this address means all link local routers. Link local means on the same LAN. So if you want to talk, you want to discover, for example, which routers are available in your neighborhood in the same LAN, you can send a message to all routers that exist on the same LAN. And the way to do that is to use this multicast address here. If you want to talk to all systems on the same LAN, you use this, the link local broadcast, which is the replacement of the 255, 255, 255, 255 that we had in IPv4. Other blocks we will discuss a bit later. The IPv6 header format is very similar to the IPv4 with a few simplifications and an expansion. It's much larger because now the address is much larger. So we have 40 bytes at least, and the IPv6 header in practice will also have many options. We'll discuss some of them a bit later. Also, one change is a change of terminology. That what was called protocol type in IPv4 is called next header, which reflects more truly what happens. Protocol type was with the old thinking that IP carries a transport layer protocol. There are multiple transport layers, so the protocol means transport layer protocol. But in reality, we may have tunnel, we can carry an IPv6 packet inside an IPv4 packet, or even an IPv6 packet inside an IPv6 packet, or even an IPv6 packet inside more complicated things for virtual private networks, things that we'll discuss in a few more weeks. So the name is next header, right? In practice, it's the same, right? It's the next protocol, but when we do Wireshark, we'll see different things. Another important difference is that in the IPv6 packet, there is a flow label, which is used to identify a flow. This is unfortunately practically not used, so the flow label is set to 0 everywhere. But the idea that is underlying is to be able to have quality of service guarantees for some flows. This is particularly true if you do an industrial network, like in a smart grid or industry automation, or when you fly by wire in an Airbus. You want that some flows are guaranteed some bandwidth. And in order to recognize the flows, the schedulers, the packet, the routers will treat those flows differently than others. We'll talk a bit about that when we talk about congestion control. We'll talk about class-based queuing. So this is an example where the flow label can be used to give a different treatment to some packets than others. Unfortunately, in the internet today, there is no agreement on how to use it. So in practice, it is not very much used yet, but it will be used later. We will come back to some of the other functions of some of the flows, of the elements of the header. We'll come back to that a bit later. Right now, let's go to a small question, one or two small questions. The background of this question is that we will sometimes need to write an address in the format of an IPv4 or an IPv6 address. So we may need to change format. For example, if I have this address, so that's an IPv4 address because it's 2 blocks of 4, so it's 32 bits written using hexa digits, like we would do it if we would invent IPv4 today. If we write it in decimal, what is it? I'll close the poll. So that was an easy question. The correct answer is A. 1, 2. So that's the first 2 hexadigits that correspond to 1 byte. So the number 1, 2 corresponds to 2, and we know that FF is 255. Right? Now an IPv6 question. What is the non-compressed version of this. I close the poll. And the majority says B, which is the correct answer. So it's very important to be able to do those mapping, because when you will analyze prefixes in particular, in routing tables, this will always come back. It's easy, but important. Okay. As you see, IP is very simple. The only difficulty is to handle the bits and the addresses. The principles are very simple. The reality is a bit more complex. And in reality, there are things that I call deviations from the architecture. The architecture is the principles, as like I give them. And one of we have seen the two principles of IP for unicast packets. Here is our first example of a deviation from the architecture. I prefer to present things using the concept that there is a clean idea at the beginning and then we deviate it from it, because this is historically how it was, and this explains why things are in this way. Network address translation is some things that the standards of internet have constantly been fighting against. They've tried to prevent it from happening because it's against the architecture. It's not something that came easily, but something that came from practice. Remember, we're in a world of software. Anything we do here, essentially, there's a lot of hardware assistance for performance, but it's all emerging from computer science. So in computer science, any programmer can decide to do things differently. And if there is a more efficient way to do it, that is perhaps ugly from an architecture viewpoint, but if it's very efficient, it will emerge. That's exactly an example here. The problem here is the problem we have with IPv4. I guess most of you, if you have an internet at home, you have IPv4 and you have one IPv4 address. Because IPv4 addresses are rare, there's not many. Even a few years ago, there were not that many. So if you want to make a block of several, you probably will be treated as an enterprise, not a private customer. And then the price of your subscription, you will need to add 1 or 2 zeros to your monthly fees for that. So it's very expensive. So you have only one address, but probably you have more than one device. You probably have a computer, a smartphone, and if you go by curiosity into your what is called the NAT here, which might be called as your ADSL modem or your Cablecom modem or your home router, this is all the same box. If you go by curiosity and look at all the IP addresses that have been allocated to visiting systems of your home, you will have the list of all people who at some point connected to you, and it might be a long list here. So you have all your smartphones, your visitor smartphone, etc. You have more than one address, and you would like to communicate in the internet. In the labs, we have another example here, which is the same thing with VirtualBox. With VirtualBox, we virtualize the physical network, but the machine, the host, has only one IP address. But then we create, with Mininet, for example, we create one or even several virtual machines. We've asked you to create one. We will use more than one IP addresses. So we may need to have more than one addresses, and we certainly have two. We have the IP address of the guest machine and of the host. So how do we use those addresses here with only one physical interface and only one physical IP address here? In addition, in VirtualBox, typically the addresses are private. Same thing at home. Your home addresses are probably private. The goal of the NAT is to make this possible. So primarily to use more than one device with a single IP address here. Of course, that deviates from the TCP-IP architecture. The principle number one is one interface is one IP address. Here we will have multiple interfaces. All those devices will use for the rest of the world the same IP address here. If you deviate from the architecture once, you must deviate more than once, because if you simply violate one rule and you do nothing else, it will break, it will not work, so things will not work. What will not work here, if you simply allocate this address and let it go and modify the source address, then what will not work is on the return path, to which machine should we go? If you give the same address to multiple machines, when they communicate, how do you know to which, to A or to B, how do you know to which of A and B the packet should go? So you need to do something else. So we will violate more than once, and what we will violate is the layering, because the NAT uses port numbers. So that's the key trick of the NAT. I'm showing here an example where I have two machines, A and B, that communicate with a UDP machine here for some, it could be TCP, that will not be very different. So this machine from the outside sees only the public address, which is called the NAT address. In the terminology here differs depending on how you read things. Here I use the terminology internal versus NAT address. So the internal addresses are the addresses of my local network. Those are the ones I see if I am sitting at the terminal of A and I do IP address show, for example, I will see this address. So that's the internal address. But for the rest of the world, I have a NAT address, which is the public address given by my internet service provider to my NAT, this one. So the server in the world that is connecting to this guy is sending a packet to this address here and to a port number, because typically we use TCP or UDP here. If we use ICMP, there's no port number, but there are other numbers inside the ICMP messages that play a similar role that can be used instead. And that what will happen is that two packets, the green packet that is destined to A, must have a different port number than the pink packet that is destined to B here. And the NAT will remember that. The NAT has a table that maps its external IP address. So in principle, you don't need this column, but sometimes NATs can have multiple external IP address and an external port number to an internal IP address and an internal port number. And the NAT swaps this, the values, changes the IP address and the port number, which is a complete violation. I mean, a middle box, a router, doesn't change the IP addresses. A router, we've done these exercises last week, when a router is the postcard principle, where if you're a switching center of the post office, you don't change the address of the postcard when you switch it to the next switching center. You keep the destination address unchanged. And the source address, same thing, because it will be needed by the destination to reply. So routers, in principle, never change the address, the IP addresses. They change the MAC addresses because they swap the packet from Ethernet to Wi-Fi, for example, but that's a different story. And a router is an intermediate system of the IP layer. Intermediate systems of a given layer, in principle, don't change the addresses of this layer, because they are the addresses they need to know what to do, and that other systems will need. But here it does. So when this packet has destination address 130, etc., UTP port, that number, the NAT will go into the table and say, oh, that's an external address. When I say external, be careful, that's the external address of a local machine. That's the external address of A, but A doesn't know it has this address. That's how the rest of the world sees A. It will go to the table, to the NAT table, and look for an exact match. Now, not the longest prefix match, but an exact match from the column NAT to the column internal. Here there is one, and it means that the port here, the only thing that helps us discriminate is the port number. So the port number 3441 means I have to go to this IP address, which is machine A. And of course, I need also to give another port number, which in that case may be the same or may be different. This is the port number that is visible in the machine A. If you do local interrogation of the machine, you want to see what is happening, you do Wireshark, etc., you will see traffic that goes to this port number and to this address here. Of course, for B, there must be another port number here, and this is how things will be differentiated. So in some sense, we use the port as an extension of the IP address. So this works only, of course, for packets that have port numbers. If the packet is encrypted, if the transport layer is encrypted, this will not work if the port number is encrypted. Yes? Speak loud, please, because you have a mask. Oh, thank you very much. That's a typo. Yes, that should be 11 here. Thank you very much. That's a typo that I will correct now. This should be number. I will not correct it now because it's too complicated to do online. But yes, that's a typo. That should be 11 here. So which addresses are translated? So again, we translate the internal address, which is the true address seen locally by this machine, to an address of this machine seen by the outside, which we call the external address or the NAT address here. Well, this is translated from the outside. If a packet comes from the outside, then it's the destination address field that is changed. And in the reverse direction, if a packet goes from the LAN to the outside, then it's the source address that is changed. And also the port number. So when a packet goes from machine B, I'll say to B because the address of A is incorrect here, goes from machine B here, then we translate this, we replace the source address here by the address of the NAT, and we must also change the port number here. We must change the port number. Why should we do that? Well, because there can be collisions. There could be, by accident, as is shown here, two machines could use exactly the same port number. In fact, since if they use the same software and do the same thing at the same time, chances are they might do exactly the same port number. In reality, it's rare because even with the same software, they're not configured exactly. So there might be services that are configured a bit differently, but this can always happen, of course. So you can never guarantee that the port number used by A is not also used by B, so you'll need to modify it here. Fortunately, the port number is 16 bits, which is a large number compared to the number of ports that I would say a PC would use. A server might be a different story, but a small normal scale PC typically uses a very small number of ports, doesn't exhaust the 16 bits of the port space here. And as I said here, so first benefit is we can reuse the same address, but another benefit is since we masquerade the IP address of the system, this address can be anything, and in particular, it can be an IP address. This is why we see lots of private IP addresses. If you're at home, you probably see an private address. If you're on the EPFL VPN, you will also see private IP addresses. In fact, most IPv4 hosts in the world use private IPv4 addresses because they are behind NATs. Now, I said that this NAT has this table, so at least I'm consistent. I put the same error everywhere. It should be a 1 here. How does it know this thing here? Of course, you can configure it manually. You can do that if your NAT is a Linux box and you use IP tables, like we'll do in one of the labs. You can do that manually. Otherwise, but of course, you would not like to do that manually. You want the thing to be plug and play. It is plug and play as long as the communication is initiated from the local side. Initiated from the local side means it is A that starts communication with S. If A starts with S, that means A must start a program, bind the program to a port number, choose a port number, and decide, for example, that I use UDP port 1029. So this is chosen by A. Then we'll send a packet to S. Now S is on the public internet, so it has a well-known port. For example, if it's an HTTP server, typically it uses port 80. So this is well known. You don't need to worry about it. then the NAT will see packets. So the NAT spies all traffic, observes all traffic that comes out, and learns from traffic that comes out. That's something that we will see in other instances. So when this sends a packet to the outside, the NAT is at the same time the default gateway, so the default router. The routing table at A will say send everything by default to NAT, which has multiple functions. It's the router at the same time as a NAT. So it receives the packet, and now it sees, oh, I must do the NAT job. So I look at the port number, which normally as a router I should not do, but I do that. And I will pick another port number for the outside, perhaps the same, or perhaps another one, depending if this one is already used. And of course, I will replace the IP address by my IP address. Now, if another system with a different address, so of course the address here should be 1 and not 0, happens to have exactly the same port number, then the NAT will be forced to choose a different port number here, 42. So NATs learn on the fly, which works only if communication is initiated from the LAN side, from the local side. I use the word LAN. Many technical references will use the terminology LAN for the local or the internal side, and WAN for the remote side. But if you use VirtualBox, for example, it doesn't make a lot of sense. I mean, the NAT of VirtualBox doesn't have a WAN. WAN means wide area network, but that's a terminology we will also find. A system that initiates a communication is usually called a client. Client-server communication, we'll talk about that a bit more when we see the transport layer. The transport layer has the concept of a client and a server. And if you want two machines to communicate together, you have a bootstrap problem for a machine to communicate with another one. It must be listening or sending. I mean, if you send a packet to another one, but the other one is not ready to receive, the thing will not work. So this is solved by having a machine, one of the two machines, playing what is called the server role. The server role means the machine is listening, is ready to receive packets. So we'll see how it's done practically in the transport layer. This is a server. A server is a machine that is running, has a program that is actively running, and it has a blocking call on receive a packet from anyone on this port number. And the server doesn't initiate the communication. The client decides when it wants to talk and sends to the server that's ready here to wait. Now, what happens if you want to put a server on your local network? Well, the NAT will not work. So you can try that. You put a server on your local network. It will not work. Well, it will not work for several reasons. Some of them are obvious. The obvious reason is how would you communicate with this server from the outside? If this server has a private address, like this 11 address, the outside cannot use it because it's a private address. It's not allowed for the outside. So you have a first problem here. And the second problem is for the NAT to work, you need communication to start from the local side, which a server will not do. So if you want to have a server behind a NAT, you need to manually configure the NAT for that. It's called, with different names, one of the versions of that is called port forwarding. Port forwarding usually means you configure in your NAT, for example, if you choose port 5000 for this server, you say to the NAT, anything that comes to you to port 5000 should go with this port or another port number and to this machine. And then you will advertise to the world a machine that has this IP address and this port number. It doesn't mean that on the NAT you have a server listening on this port number, but it means that you have a server somewhere else here. So this is a drawback, and in particular, applications that are peer-to-peer. Peer-to-peer means that both roles, client and server, are played at the same time by the same machine. A web server is a server. A web navigator, like Firefox, is a client. It contacts the web server, and the web server is waiting for requests to come. But when you do Skype, if I call you, or you call me, I mean, none of us is a server, or both of us have the server role, if you want. We should be waiting for calls to come here. So if you use Skype, you're de facto putting a server behind your NAT. But, so one way is to do port forwarding in your NAT by analyzing the Skype, doing Wireshark on Skype to see which ports it uses. But Skype would not work if you would need to do port forwarding. So Skype has methods to do that, and in particular, the methods involve intermediate servers. So most of the time when Skype A talks to Skype B, we go via an intermediate server. So the server communication, you will first play the client role, and then you will communicate with the server, and then your Skype device will periodically pull the server here with a client role as well, so in order to be able to make the appropriate mappings in the NATs. This is called sometimes punching a hole in the NAT, making the NAT work here. So you need to configure servers, which is a pain, but is also a benefit. This is also a protection to servers. 20 years ago, it was easy to put a server on the internet. Doing it today is very tricky. What happens if you put a server and you make it publicly available? In the following seconds, it is bombarded with attacks. So port scans, as soon as one port is found to be open, there are robots in the internet that will try to send traffic to this port. And those robots will try all the different weaknesses that have been found in different versions of operating system. And if you have an unpatched operating system that has the weakness, they will be able to exploit this weakness and take control of your server. So this, if you have a server on the internet, you must be very careful. You must certainly patch it every week to have the latest version of the operating system to make sure it's not vulnerable, or at least vulnerable only to extremely to unknown attacks called zero-day attacks. And second, you should have a monitoring system to see what happens, to make sure you are aware if your system is attacked. So you don't want my and your PC and our smartphone to be exposed to that. So this is the need to do port forwarding means that if you put a server here, you need to explicitly make it available and only at the ports that you decide here. A machine has, a Linux machine has a number of ports that are open, few. A Windows machine has zillions of ports open that do zillions of things with zillions of other servers. So there's a lot of, when you do Wireshark on a Mac or a Windows machine, you will be surprised to see all the things that happen. So there's a lot of traffic that happens. But this is all in client mode. So the NAT protects your machine because it allows operation only once it is started from this side. So the NAT has two functions. First, it allows to reuse one address more than once, but also it provides a protection function for servers. Everything I said was for IPv4. In theory, you can do the same thing for IPv6. But if you think about it, the need for NATs with IPv6 disappears because IPv6 with this astronomically long prefix. So we don't expect that the provider would be so mean to give you only one IPv6 address. So you expect from providers that they give you not one IP address, but a block of at least, for example, 16 IP addresses. Or 16 would mean they reserve one hexadecimal digit for your own subnet part. This is what happened here, for example. I received from my service provider a prefix of size 60. That means that the last hex digit of this is available for me. And I can have, for example, 16 different IP addresses here, which is probably the minimum you get from an IPv6 provider. If you get that, then there is no need to do a NAT. NAT for IPv6 exists. You can do it, and with IP table, you can do it manually. There's also some software that does it, but in principle, your home router will not do it for IPv6 because there's no need. Which means that your IPv6 address that you receive on your local network will be a global, unique address, not a local address, not a private address here. which carries also some benefits, but also some problems. It's easier to put a server, but then you have also this lack of protection problem. The lack of protection is usually provided by the fact that your home router, if it provides you an IPv6 service that it gets from a server, will act as a filtering router. It will not allow communication with your IPv6 hosts unless it started from the inside here. So it will do the same as if it would be a NAT, but now not because you want to multiplex one address to many, but for protection. Another problem is that your IP address becomes visible. One benefit of having private addresses is that everybody has the same. So 192.168 address, we probably have one similar address. It reflects more the version of the home, the ADSL modem that you're using, so which sub-block in that it uses, more than who you are. So it doesn't reveal much about you. If you have a globally unique address that you use all the time, that is, of course, revealing a lot about your system. So all data mining entities on the internet will know exactly what is your IP address. So you may want to hide that. So this is why Linux, Mac at least, and Windows operating systems will give what is called temporary temporary addresses that change all the time. So they will constantly change your IP address so that somebody who's trying to track you will not be able to know what your IP address is. We'll talk about that in a few more minutes. What I said is the simple story of the NAT. The true story is ugly. So in the previous slide, I showed that a NAT has to do a mapping. It has to transform an internal address, so the local address that my device has at home, and a port number to a NAT address and a NAT port number. The NAT address is typically the only IP address that the NAT has, and the NAT port number is one that it has chosen. That's what I've shown here. Such a NAT is called a full cone. Terminology is typical of computer science, it's a bit contorted, but okay. Some other NATs do, so a full cone is a friendly to external correspondent, because that means once you know the port number and the this port number here, it can be used by, so the mapping is always the same, right? So if the machine, the local machine, speaks to several machines to the outside on the same port number, the different machines will always see this with the same exactly combination of address and port number. So for example, for Skype, if the Skype server sees your Skype client at home, it sees this port number here, the NAT port number. It can give this information to your Skype correspondent, who can then talk directly to you without going through the Skype server, which is good for Skype because that means Skype does not need to do store and forward. We've seen last week the store and forward is expensive because you need huge buffers. You need to buffer the entire conversation rather than just individual IP packets. So that's good for things. But not all NATs are like this. So many NATs do more complex things, also for security reasons. They allocate a port number differently for every external correspondent. That is more secure. That means if someone found a way to communicate with you, someone else cannot learn from that because it will not work. In the NAT mapping table, the port number will be, the NAT will validate whether it comes from a given external address and port, and if not, it will not allow to forward the thing. This is more secure, but it means that things like Skype don't work in peer-to-peer mode. You need to go through a server. And also things like Teredo will have a hard time working. In practice, we found that many Miredo systems that we work don't always work well. This is because of symmetric NATs, typically. NATs can be concatenated. So if you work at home and you put the virtual box at home, you will have the NAT of the virtual machine that is behind the NAT of your home. And if in addition you are on the private network of EPFL, you are beyond the NAT of EPFL because EPFL provides the VPN through a NAT. What kind of NAT is that? That's a carrier-grade NAT. Carrier-grade NAT, carrier-grade means big. Carrier means ISP, Internet Service Provider. Carrier-grade means it's a big NAT, not just like the little box we have at home. We can use the same principle of NAT to share not just one address, but a number of addresses. So if I have a block of P addresses, I can share those P addresses to N much larger than P using the same trick. This is what EPFL does, for example. EPFL has a number of public IPv4 addresses that are mapped to the 10/8 subnets of EPFL, which are the addresses that are given when you're on the VPN here. So when I'm on the VPN of EPFL, for example, I see a 10.something address, but the outside world will not see it. You can go to some sites. What is my IP address? You can do this test. You will see that this is mapped here. Voila, that's all for today. Thank you very much, and see you in person in, I'm not sure, perhaps in 2 weeks in the lab.